Hello, good afternoon. Hey, I'm going to present about a real-time architecture using Hadoop and Storm. Who am I? I am Nathan Bijnens. I'm a big data consultant in Belgium, and I have some experience with Hadoop and Storm, and as well as with Puppet and system engineering and various things. So maybe just to put it into context, I guess everyone has heard of the 3 V's, but it might be interesting to refresh them again. So let's talk about volume. How much data do you have at the moment? And how much data do you think you will have in the next year, in the next 5 years? And I've read it somewhere, not sure about it where, that there will be 44 times as much data in 2015 than there was in 2012. And if we think about where is all this data, it's in different kind of systems, and it's ever increasing. So with the coming of the Internet of Things, data will only increase. So when every device has a sensor and will generate data, we will need to store and process this one. So and we have at the same time more traditional systems can't really cope with this volume. The next one is velocity. And it's beginning to become much more important to get from reactive analytics to go to predictive and even prescriptive analytics. So for fraud detection, energy or market allocations, marketing campaigns, and so on and so on. So it's even harder to scale. It's even harder to cope with the velocity of incoming data and lots of incoming data than it was with just the volume, because you could all put it on a SAN or something, but that really won't scale your systems. And the last V is of course variety. About even less than 20% of all data is structured. What's in your relational databases. It's only really a small part of the data of your organization. Even more than 80% of all data is probably unstructured. So what are the new data sources? Word documents, emails, tweets, APIs. There's lots of data locked into several APIs. So the variety of data has much increased, as well as there are new kinds of data, like video data and photos, and it's so traditional systems have it quite hard to cope with these newer, rarer forms of data, and the storage is one thing, but the processing thing is another, and even. If we look at the computing trends of today, of the past, then we saw that computations, CPUs and so on, were really expensive. The same goes for disk storage and memory. It was all quite expensive until recently. But coordination was actually quite easy. If you had one big box, coordination is really easy. But the current situation, that changed all. So computation is quite cheap. We have many core computers. It's easy to start new, to get clustered systems. So you will connect many computers with many core CPUs. Disk storage has really become cheap. I mean, you can get a 4 terabyte disk for under €70 today. Memory is becoming cheaper and cheaper, especially if you compare that to the past. But coordination is becoming much more difficult. because if you acquire a lock on something, all those other processes have to wait. So you will have a lot of idle time, and that's really not really making a good use of your resources. A lot of what I'm going to tell you about are unfortunately not my ideas, but the ideas of Nathan Marz. He used to be an engineer at Twitter and Backtype, but he's now creating a startup, but it's still not really public what he's going to do. And he's the creator of the Storm processor, as well as Cascalog, which is a closure fork for cascading, and ElephantDB. And he's writing a really interesting book, the Big Data book, and it's Manning is publishing it, and I think it will take another half year before it actually gets published. And every couple of months it gets pushed back for another 6 months. And what he's actually writing in his book is about a data system. And a data system, so let's first talk about what data really is. Not all information is created equally, because some information is derived and aggregated from other sources. So if you look at the account balance, sometimes I look at my account and I will see one number, but this number is actually the aggregation of all previous transactions that happened from the beginning of the account till now. So the same goes for the number of followers or your current friend list on Facebook. It's actually all people that ever followed you and all people that unfollowed you. So, but it's actually really interesting to keep the original information, to keep and to dig deeper to the most raw form. And if you go from the most raw form, that's actually what we call data. That's the thing, you can't really go any deeper. So that's very similar to an event. So the actual following event. And everything we actually do generates data. So if you pay with your credit card, you pass through, you swipe through the tube, you buy a movie, you listen to a song, you just walk around, and in the future, people with Google Glass, it will all be events. And where in the past, events used to manipulate the master data set. So in the past, there would be updates and most of the original information would get lost. Today, the events are the master data. And so let's store those events. This is really a different setup than we used to work, because disks has become a lot cheaper. So that's one thing. And even more important, this data or event is immutable. It can't be changed because it's always true. At that time, it's always, this transaction is always true. Actually, that's something that we software engineers can learn from accountants, because if they delete their records, they get sued or go to prison, maybe. And of course, data is time-based, because for it to be true, for it to be always true, an event should have happened on a precise time, because otherwise. And because it's time-based, you can always regenerate a state. Like, what was my bank balance on the 1st of May 2005, or what was it yesterday? And that could have happened thousands more or millions more of transactions, but you can always go back to a state of the past. It would be really interesting if you could go to a state of the future, but that's not for this talk. So if you look at the capturing change traditionally, then it would just be an update. So let's say I moved from Antwerp to Ghent, then I would have updated the record in the table. And what if you denormalized it? Then you would have probably, this is a really nice normalized table, but let's say that for some reasons you denormalized it, which probably is the case, or have it in caches, then you should invalidate and update it as well. So that's a lot harder. But actually, and capturing chains now is just add another record and then and solve the problem of what's the current status. That's the second step. So the actual data you query is often transformed or aggregated because it's only in rare cases that you're actually interested in the transactions or events themselves. Most of the time it's the aggregated form. And this can we describe as a query is actually a pure function in the mathematical sense that you take on all the data as input, and this will generate the answer. But of course, different functions may look at different portions of the data and aggregate it in completely different ways. So let's say I'm interested in the number of people living in each city, then I would just aggregate it and I would have an easy aggregation and would just account. But if you have millions or billions of records, then it's probably going quite slow. So you will have to do some pre-computations because it might be petabyte scale. And maybe if sometimes you might ask, yeah, isn't that why there are NoSQL databases or things like Impala or Drill? Probably they can help, but they aren't really, but if it's just raw events, then it will still be too slow because you will probably have more than billions of events. So what I'm proposing is a layered architecture with a batch layer, with a speed layer, and with a serving layer. And if I draw it out a bit, then we have our batch layer in the bottom that will keep all our data. We will have a small speed layer on top that will just process the last couple of hours. And then we will have a serving layer that just merge the two, merge the results of both of them. So let's first talk a bit about the batch layer. A small overview. And the batch layer is, a property of the batch layer is really unrestrained computation. You can calculate anything with the batch layer. Of course, if you have enough time. But actually any sort of calculation you should be able to do in the batch layer. And there's no need to denormalize your data because you're storing the events. It's actually just a master copy of your data. Why are we denormalizing? That's probably because we're rewriting our storage to query it faster, but that we will solve that in a different way. So our batch layer needs to be horizontal scalable because we will have lots of data at the moment, but we will have even more data in the future. And it can be high latency, so it might take a while till when we get results, but let's pretend that that doesn't really matter at the moment. And maybe really important, the functional computation based on immutable inputs, will always give the same results. So you can always recalculate. And the batch layer will store the master copy of the data set in an append-only manner. So I think Hadoop might be a good match because actually it doesn't really matter which technologies you use, but I think this architecture calls for a distributed file system combined with some kind of processing framework on top of it. So if you want to use Spark, fine by me. If you want to use something else, doesn't really matter, but I think Hadoop is a really good match for it. So we will generate some views, and in the views, what will actually happen is that so we start from our master data set. We will run some computations on top of it. That will be our MapReduce functions, and those will generate some views. Maybe a quick reminder of what MapReduce is. So we are going to take a large data set and we'll divide it into some subsets. Then we will calculate, perform the same function on all subsets, and the output of that function, the output of all those functions, we will recombine it, and that's MapReduce. And often it will be split up in mostly multiple jobs, especially if you want to do joins and so on. So we want to be as resilient to failure as possible. So actually serialization and schemas are quite, provides structural integrity. It's if you're going to store really your master data set, it's really important to detect the corruption as fast as possible. And it's better to detect it at write time than at read time, because at write time you probably can do something about it, but at read time it will be much, much harder. So CSVs, or common separated text, is probably is also a serialization format, but it's a really poorly defined one. Other serialization formats that could be used, like Drift or Avro or protocol buffers, doesn't really matter which one, but or even others, doesn't matter, and it will be a lot faster and use less space even. You can use compression with it as well. And the batch views will be read-only. They will be written in batch, but the querying of it will be just read-only. And we will, on every iteration of our MapReduce process, we will just generate the views from scratch. This allows, maybe you can always do some optimizations, but it's important that you always can regenerate any state you want. Because, yeah, if you're, that's an essential property, that you can always just regenerate your views. But of course, it might be that that some of your MapReduce processes will be too slow. So it could be that you could split it up and have maybe some shortcuts like an incremental update or something. That's all possible. So there are a few batch view databases like ElephantDB. ElephantDB is a sort of key value store that with a Berkeley DB backend, which actually which doesn't allow updates or writes to it. It gets the only way to update it is to have a MapReduce process generate a couple of files and point your ElephantDB cluster to your HDFS location, where it can find the new indexes, and then it will read those indexes and replace the old ones. Another one is Splout, same principle, but with a SQL backend. Both ElephantDB and Splout and Voldemort do shard it themselves. And Voldemort, which can be updated, is written by LinkedIn, but they have a read-only backend, so that might be as well usable or useful. But we're not done yet. So we have all our incoming data. Well, not all our incoming data is absorbed in our batch views. the largest part of our history is already absorbed, but there will always be a part that's not yet absorbed, because the data that gets saved is actually quite, it's actually only going to be saved quite slowly, because our MapReduce processes could take hours or even days to complete. So we will always have a gap of data that's not really yet absorbed. But the good thing is, if we have terabytes of data, this might only be gigabytes of data, so we can use other tools for that. And one of those tools might be the speed layer. And the speed layer, well, we're having our, this is the thing we just discussed. If there are any questions, you can interrupt me, that's no problem. And then we're going to talk about the speed layer at the moment. The speed layer is, what I'm going to talk about is it's using a stream processing layer, but you could use, what you actually also could do is just have a relational database as your speed layer. Why not? Because all data is actually written to your batch layer as well. So it doesn't really matter if your system can go, if the speed layer, if the data disappears after a while, or that it can crash, or that and because the data will be much less, will only be the hours worth or days worth of data. You can use different tools that might be that, for example, keep everything in memory. Why not? So, but I think if you want to do a bit more processing and pre-processing on your data, then I think something like stream processing will be a good match, especially if you have large digests of data coming in. So that's stream processing, and it will be a continuous process. So if let's say that we have a counter or something, then we will just maybe have a sliding window, and then within the sliding window just increase the counts or something. But of course, some things will be a bit harder to calculate in a streaming fashion than we could. In the batch layer, we literally can calculate anything, but in the streaming layer, some calculations will be a lot harder. Like a unique count, you can mostly do just estimations. The speed layer can be transactional, and in some circumstances this can be really interesting, because you might, if you're counting, then it might be interesting to have exactly once schematics and so on. But it's only for a limited window. So just for those last couple of hours, or the last day of data. And the good thing is, all the complexity of the data system is isolated in this layer. So we can always, so you can do a bit more crazy stuff into the speed. You can you can do some estimations, but if it crashes, there won't really be data loss, because this layer is actually just a throwaway. The logic isn't throwaway, but the data of this layer is throwaway. So if you have, so the speed layer gives also a choice between cap. So what's cap again? So you have consistency, so all the nodes see the same data at the same time, or you have availability. So that's guaranteed that every request receives a response. And you have partitioning tolerance. The system continues to operate despite message loss or failures of parts of the system, network loss, machine failures. The last one, you can't really sacrifice partition tolerance, because you might, if you have a distributed system where none of the components can fail, well, you will have a really hard time keeping it up. And because of of this model, you have the active choice between availability and consistency, which is different than if you just would have chosen for Cassandra or HBase or something. Well, you might use those, of course, in this system. Eventual accuracy. So in your speed layer, because you don't really have all the data of the past, you can't really do anything. You can't do all kinds of calculations. So doing a unique count will be hard. You can do an estimation, but it will never be exactly right. The same goes for machine learning. Lots of algorithms require that you have lots of data first. But what you could do is you could create a model using your batch layer and just apply it in your speed layer. And the batch layer on the next run, it will update the model. So these kinds of things can the speed. So your speed layer, you will make some trade-offs to get to the point where so that it's fast, because you don't really have all the data. It's like viewing a video on YouTube. So if you viewed it, the counter goes up, but actually the numbers behind it aren't the real numbers. They get only updated once every often, and every number in between such an update is actually just an estimation. It has been viewed that many times the last couple of hours. Okay, let's say, okay, just increase the number that we just showed with a little bit. So it's used in lots of places. So this is our speed layer again. And I think Storm is like Hadoop for the batch layer. I think Storm is a good fit for the speed layer, because we have message passing. It is distributed, and it's also scalable. But actually, those things can be useful, but are not really required for this. It's incremental, which for some algorithms like those counts is really useful, and it's data in motion. So what are the components of Storm? So the Nimbus is a bit like the job tracker in Hadoop. It does some coordination, and it communicates with Zookeeper. The supervisors, they manage the workers. Those are a bit like the task tracker. They communicate using Zookeeper as well. And then we have every supervisor will launch executors, which are physical GVM processes. And on those executors will actually several threads be for each bolt or spout, each processing unit, a new thread will be started. And the actual executors in the actual bolts and spouts, those will process the stream. What's the data model of Storm? Are actually tuples, and a tuple is a named list of values, dynamically typed, and a stream is just a sequence of tuples. In Storm you have spouts and bolts. A spout is a source of the data streams, and some spouts can repeat the data stream if something went wrong downstream. So if you had let me first tell you what a bolt2. Bolt2 is actually a stream transformation. It has at least one input stream and 0 or more output streams. And you can have transactional topologies. So you will have a tuple, and the tuple will get processed by, will get outputted by the spout, and will get processed by a couple of bolts. And let's say the machine where bolt X is running goes down, then the bolt right before that won't get an acknowledge, so it will communicate that back to the spout, and the spout might be able to repeat the message. Not all spouts do that, but if you would use Kafka in combination with Storm, then it might work. Then this works quite well. Or if you have an exception in a bolt, then the whole stream can be repeated. But of course, if it gets repeated, then you should always look out, because you don't really get, the spout gets a message that it's getting replayed, but your bolts should look for it actually. And you can do groupings, so you can have multiple output streams. Both the bolts and spouts can have multiple output streams, but they can be recombined. You can have a bolt that has multiple input streams, which allows for a sort of sliding window joining, which can be useful at times. And then at the data ingestion side, I see what is quite often the case is that it's at streaming, that we're making use of queuing like Kafka or RabbitMQ or Kestrel or even Flume or Scribe. And the output of our Storm process will actually need to be written in some kind of read and write database. It needs to be readable and writable, random access. But so those kind of databases are much more complex than just our read-only views, because there can be multiple updates at the same time for the same key and so on. A couple of choices we've used in the past were Cassandra and Redis, but depending on your use case, Elasticsearch might be a good match, or why not even just a relational database? Why not? It can work, because everything in the speed layer will get discarded once the batch layer has processed the data. Everything the speed layer has done gets discarded. So then we have the serving layer. And in the serving layer, we will combine the outputs of our two layers. And the serving layer will, of course, have to answer random reads. And so the serving layer needs to be able to answer any query that, in a short amount of time. So it will access our pre-computed views for the batch in real time and merge those. So a really easy schematic. But of course, it's always hard. Some things require that you adjust. How would you calculate an average? You can't really combine two averages, or not that easy. So it's better to just store the sums and counts separately in each layer and then just combine them in the last step, for example. Or for unique counts, your batch layer can calculate a unique count, and then you could combine it with the estimation of your speed layer. So the answer you will get might be accurate. If it needs to be accurate for your use case, you can make it accurate, but it will cost more memory and so on, and more processing power, because your speed layer. So especially for a unique count, you will have to keep a lot more data available in memory and queryable. So a small overview of our architecture. So we have our incoming data. This could coming from a queue or Kafka or something. With our batch layer, with Hadoop and ElephantDB or anything, or Spark and so on. And on the top we have Storm combined with Cassandra, and then our query layer, and that's a bit the Lambda architecture. And the name Lambda was actually first coined by Alonzo Church. While he needed a Greek letter for the functional, for his theory of functional abstraction that he wrote in the 1930s, and Nathan Marz thought that it was a good idea to use this number, to use this letter, because it's actually, and what we actually see is that a lot of those things that we talked about, like immutable data, and this actually come from the functional world. I think both Nathan Marz and Google have looked quite a lot to the Lisp world and to other functional languages. Even if you ever read the MapReduce paper, then of Google, then in maybe not the first, but in the introduction, that says, yeah, it's actually just those functional concepts of those functional languages, but applied on a much larger scale. The Lambda architecture, well, it can discard any view, both from the batch and real-time layer, and just recreate everything from the master data. So there's a really high tolerance for human and system mistakes. As long as you don't delete your master dataset, as long as your master dataset isn't corrupted, you can just regenerate everything, which is a nice thing to have, because it might solve a lot of, because it's only because it's append only, the chances of data corruption are much lower, so that's a good thing. Mistakes in this architecture are just corrected because you can recompute it. So if you have a bug in your view generation, you just recompute it. Anti-data storage is actually highly optimized, because you keep your master dataset, your events, your rawest form, you just keep it on disk. You don't keep it in memory, so it can be, so disk storage is cheap, but memory is still a lot more expensive, and it will be always more expensive than disk storage. So because of this, you can keep a lot more data, and you just keep in memory the things you will actually query for. But if you later on realize that you wanted to query more, that you maybe wanted to do some other analytics than you did before, you can always just generate the new views using those with those new insights, because you have your original data set. And this immutability changes everything, actually, because so I think keeping your master data set and your events immutable gives so much possibilities in regeneration, in new insights in the future, as well as having a much more higher fault tolerance. That is worthwhile to look into, how you can have your well, it's worth changing things to make things more immutable. Thank you for listening. Yeah, and if you have any questions, you can always find me on Twitter, or if you want to email me, that's fine. Or I will be here today and tomorrow. Just come and talk to me. I'm always interested.